Now, what is data? I would say it is the most important aspect of any Six Sigma project, right? So data is a numerical number, numerical expression of an activity, right? And data collection is an integral part of Six Sigma. So what is the sources? You do the actual observation, or you collect the historical data, wherein you check the record. Why collect the data? It's a common language. Decision stand the test of time. I mean, it's a no-brainer. Rather than I know, versus it takes into account it takes out the personal bias from the equation. Rather than saying I think it is something, you'll be able to say I know because you have a data which has proved that. So there are various data collection techniques. So one technique is, this data collection plan that I showed you, wherein you can clearly categorize and mention what are we measuring, why do we measure it. You can use check sheets to measure, to collect the data. You can prepare a time and motion sheet, wherein you can give it to processor who would fill in the time and motion to collect the data and give it to you. Okay, then the operational definition. Operational definition is clearly, it's a description of what is being measured and what is being analyzed. So it's a kind of paragraph. In English, you're trying to define what you're trying to measure. Wherever possible, if you're trying to measure something, you put in the formula for that particular measurement as well, so that there is no ambiguity. Everybody in the project is clear to exactly what should be collected. Right, and then you would do baselining of the data. You would baseline what is the current performance of the process that you're trying to improve. And again, baselining you can do only when you have the data available. So which you can collect by doing time and motion, check sheet, or data collection plan, giving it to everyone. And your baselining should be able to answer a few vital questions. One is it is it sure that the problem exists? What is the current process capability in terms of the sigma level? Have you already identified any potential cause? Is the baseline far away from the targeted value that we have taken, or is it same as the agreed target? If it is same as agreed target, we really don't need to do the project, right? And at the time of baselining, you would be able to find out, is it necessary to do this particular project, right? So if we believe that something is wrong and the data tells us otherwise, then we need to take a decision, whether we should go ahead with the project or not. Okay, so let's come to the data type, and I will flip over to my other presentation. So what are data types? So any data in the world, you can categorize into two types. One is a continuous data. Continuous data is a data that can be expressed in fractions. Okay, so if I would, Scott, you're still there, right?
I am still here.
Okay, great. So continuous data is a data that can be expressed in fractions. So in other words, even if you break down that particular data, the meaning would not change. So I'll give an example. Suppose we are trying to measure the time, the duration for this entire training. So let's say we say 16 hours. Okay, or let's say for the ease of calculation, let's say 10 hours. Okay, so 10 hours, I can break it down and I can say, what, 600 minutes?
Mm-hmm. Exactly.
So I have broken it down, but I'm still talking about the duration, right? And I can convert it into seconds as well, milliseconds as well. Till the time I'm able to convert it, and the meaning would not change. I can break down the data into finer refinements, and I can measure it on a scale. It is a continuous data. Everything else is discrete. Discrete is something that I can count. Remember, we calculated defect per million opportunity, right? Wherein we were able to count the defects. So that is a discrete data set. Anything which is not continuous is a discrete. It is something that we cannot break down. If you break it down, the meaning would change. It is a data that is expressed as a whole value, a whole number, right? So we cannot measure it on a scale or a continuum. Okay, is the definition clear about continuous and discrete? Very important, because all the further hypothesis or statistical analysis would be based on the data type that we have.
Okay. Yeah, I think so.
Okay, perfect. Some examples to make it much more clear. Continuous data, process yield, height of a person. So height, you measure it in what? Feet, centimeter, right? You can break it down into, sorry, meter. You can break it down into centimeter, millimeter, right? And then you have cycle times, which are expressed in hours, days, weeks, months, minutes, effort variance, which is percentage deviation, schedule variance. All this is an example of, what do you think it is an example of, continuous or discrete?
Continuous.
Continuous. Perfect. And discrete, days in the week. So how many days are there in the week? 7 days. It's a count. Number of yes responses to a survey. You can count the yes responses.
Yep.
Number of countries that play cricket. Categories like, so the survey that you take, CSAT rating that you take, 1, 2, 3, 4, 5, right? Categories like machine 1, machine 2, machine 3, yes, no, pass, fail, all the binary data. That is an example of discrete data set.
Right.
Okay. So
Yep.
small exercise for you, Scott. So if you can think of, from wherever you are sitting, if you can look around and think of uh, two continuous and two discrete data sets.
Two continuous. Time
Okay.
is a continuous,
Mm-hmm.
as well as average handle time.
Average handling time. All
Yep.
right. How about discrete?
Let's see if I have anything discrete. Calls received,
Yes.
because
You can count them.
it's a defined number.
Right.
Or people absent.
People absent. Absolutely, because it's again the number. I'll go back to time. So when you say time, how do you express it?
You had hours, minutes, seconds. You can
Right.
break it down by different
Yes.
pieces.
Right. Absolutely. So that's the example for continuous and discrete. Now, as a black belt or as a green belt or as a Six Sigma professional, it is very important for you to understand and learn how would you convert discrete data to a continuous data set. So, for example, uh, average. So, let's say I am, and there is something known as pseudo continuous as well, which is out of the syllabus. But then I'll just tell you about it. Pseudo continuous is a data which is not actually continuous, but then you can consider it as a continuous and you can use it, right? So for example, many people say percentage is not continuous but it's discrete, but you can use percentage in a continuous as well. So that's the reason why you see yield of the process, we have taken it in an example of a continuous data set. All right.
Right.
Okay, I will. Okay, some more example. Temperature of the room. Right. I generally ask the participants, do you think it's a continuous or a discrete data?
Are you there?
Yeah. Scott, can you hear me?
Yep. Now I can. I think I lost you for a second.
Oh, as long as it was for a second, I'm okay with it. So, temperature of the room. I was asking, do you think it's a continuous data or a discrete data set?
Discrete.
Right.
Oh,
Okay. Now, why discrete?
because the temperature of the room is the temperature of the room, it's 75 degrees.
Right. Right. You cannot actually break it down, right? But then
Right.
the other definition which says, you can measure it on a continuum or a scale, you can, probably do that. So again, there's some ambiguity there. But then, statistics says wherever possible use continuous data. So we actually make it a pseudo continuous and we use it.
Okay.
Exchange rate of a currency.
Exchange rate of a currency. Yeah, it would be, exchange rate would be continuous.
Yes. So, if you are saying dollars, you can probably break it down into cents.
Right. Right.
Right. Lateness of delivery.
Discrete. Well, lateness of a delivery could go hours, minutes, days.
Absolutely.
So you could break it down. Continuous.
Number of deliveries late would be discrete.
Right. Yeah.
Right. Height of the person.
Continuous.
Absolutely. So we have so many slides on data type. So let's go over it. Right. So I would say from the list, give me 4 continuous, 4 discrete. I don't even know if there are 4 discrete. Let's find out.
All right. Errors on a report would be discrete.
Right.
Percent on time payment invoices would be percent on time would be discrete.
Right.
With the
But you can use it as a continuous as well.
Could go the other way.
Yeah.
Width of a sheet would be continuous. Number of liners thin. I have no idea what that is. I'm gonna skip it. Number of invoices rejected. Discrete.
Discrete. Yep.
Number of bugs in a program. Discrete. Number of trainees in the class. Discrete. Lead time required to respond to a customer's complaint. Lead time. That would be continuous.
Yep.
Time taken to process a purchase order. Continuous. Out of 100 sheets, the number that met the thickness of 100 sheets would be discrete.
Yeah. So this one is tricky. You can use it either ways. So it is asking out of 100 sheets, the number that meets the thickness 4 plus minus 0.9. So let's say if the number is 50, right? So 50 divided by 100, right, will give me 50%. It can be continuous, right? And if I count the sheet 50, it is a discrete data set.
Yeah, that's fun.
Right.
Number of suitcases lost would be discrete.
And they continue to do that. So.
Continuous if you wanted it to be percentage, right?
Right. Number of suitcases lost per day, right? It's a continuous.
Right.
Per week, it's a continuous.
Right.
Right. I think you got it. So we'll not go
to
the ones on the right hand side, unless you want to go through it. I am okay with it.
No, I'm good. I think I'm good.
Okay, perfect. So let's move ahead. So for a continuous data set, since you would be able to measure it, you can actually look at the measure of centering and dispersion, right? Because here you would be able to calculate what is the median, what is the mean, what is the mode. You would be able to calculate the standard deviation, variance, and range, right? But when it is count, you would not be able to calculate the count, the standard deviation of the count and the range. You would be able to, but it will not be correct. Okay. You know how to calculate.
Can we do that one more time? I think it was breaking up.
Okay. This slide?
Yeah, just this slide.
Okay. All right. So what I was saying, if you have a continuous data, right, you would be able to calculate the measure of central tendency and the measure of dispersion both, since it's something that you can measure. So you can calculate the average, you can calculate the median, and you can calculate the mode.
Okay.
Right? And you can calculate standard deviation, variance, and range. Right? But then if it's a discrete data, you would not be able to calculate the mean, median, and mode. You would not be able to calculate the distance, right? Because it is a count. So the
Right.
standard deviation, etc., cannot be calculated, right? So depending on the data type, you would be able to calculate the capability of the process. So if it's a discrete data, you would go the DPMO route and you would calculate the DPMO value from there. And if it's a continuous data, you would calculate the sigma score or the Z value. And we will learn, how do we calculate that.
Okay.
Okay. Descriptive statistics. So descriptive statistics, it's so what is descriptive? It is something that is describing the statistics that we have. So it will reveal the information about the data, the spread of the data. The spread is the dispersion and the variation of the data. It will talk about the shape of the data distribution. And the measure of is kurtosis and skewness. And then the approximate centering of the data, which is mean, median, and mode. We will look at all these. Okay. So measure of central tendency, there are 3 measures. Do you remember it?
Yep.
What are those? Is there an each and every slide? So, Scott, what are the 3 measures of centering?
Mean, meridian, and mode.
Mean, median, mode. And what are the median. 3 measures of spread?
You got your range and your standard deviation.
Yeah, and variance. Okay. So you understood the concept of Six Sigma, right? So we know that Six Sigma is all about reduction of variation. Okay, we need to shrink the process as much as possible. Okay.
Yep.
There would never be a situation where the variation would be equal to 0. There would always be some variation in the process. If you have a process where variation is equal to 0, something is wrong. Okay, it is not possible. So it might have, there might be some difference even in automation. Even if you have automated a process, there might be some variation probably after 10 decimal place, but there would be some variation or the other. So the variation, you can broadly categorize the variation into 2 types. One is the common cause variation, something that exists in the process naturally. And then there's another one, which is the special cause variation, right? So if you remember the pilot A example of that aircraft, pilot A, him behaving or the variation that he's doing within the specification range, it's a common cause variation. Normally he's varying like that. Okay. And the special cause is, pilot B, his common cause variation is within that small circle where he has always landed. And one time he has landed outside that. That's a special cause. Something special happened on that particular day. Okay. So these are the 2 kind of variations. And, so as a Six Sigma professional, you would need to understand, what is the normal or the common cause variation and what is the special cause variation. If special cause variation starts happening too many times in the process, it would become a common cause variation. Right, because it's not special anymore. It is happening way too often.
Okay.
Right?
Right.
Okay. Now, I will come on to a concept of normal and not normal data. So what is normal data? Statistically, a normal distribution or a normal data is a data where mean is equal to median is equal to mode. You saw this example here. Mean was 2000. Median
2000
is again 2000.
Yep.
And mode is again 2000. right? Perfect scenario.
Mm-hmm.
You would always see this scenario in training, only in training.
I was going to say it doesn't. It can't happen very often.
It would never happen. Believe me, it will never happen. Uh, so that's the reason why I say, you would never find a perfect normal distribution. It is not possible. That means data is skewed, right? There's somebody had doctored the data, right? So perfect normal distribution doesn't exist practically. Okay, what will happen is that it would be a normal distribution. Mean, median, and mode would be very close to each other in normal distribution.
Yes.
Okay, and normally what you would see is always a not normal distribution. So then there is a concept of central limit theorem that will that we will apply to convert that into a normal distribution. Unfortunately, in statistics, there are a lot of analysis, lot of tests available for normal distribution. For not normal distribution, there are very limited tests available, right? So entire statistics has been written assuming that the distribution is normal. So when they say in long term, everything law of averages comes into picture and everything becomes normal. So that's the reason why all the tests, all the analysis that you would see, all the formulas that you would see would assume that the data distribution is normal. So if we do get a not normal distribution, we have to convert that not normal into a normal distribution wherever we can. If we cannot do that, then we would live with not normal distribution and we would apply the relevant test. Okay, the one that you see, the one that I've highlighted is for normal distribution. It's a perfect bell curve. Mean is exactly at the center. It is cutting the bell curve into half. Both are mirror images, right? Mean is, the height. Mean is exactly at the center. So the bell curve, the height at the mean is the highest.
Mm-hmm.
These two lines that you see here, although it is looking like it is touching the x-axis, but it will never touch the x-axis. At some point of time, it will become parallel.
Mm-hmm.
Okay.
Right.
Now for skewed distribution, so it can be a left skewed or it can be a right skewed. Okay. In a skewed distribution, your median, there would be difference between mean, median, and mode. So if you see here, if there are a lot of data points towards this side,
right,
okay, and the tail goes longer here.
Mm-hmm.
Sorry, my mistake. The tail is longer here, so that means there are a lot of data points reflecting here. So mean has shifted towards this side because there are more data points here, right? The median is here. There would be different. So wherever there would be more data points, mean will shift towards that side. Okay, and if there is a significant difference between these two, that means your distribution is skewed. Visually, you would be able to see it by looking at the bell curve. If you see this bell curve is not exactly in the middle. So you know that this distribution is skewed.
Okay.
Skewness would mean that the height of the bell curve is either towards the left hand side or right hand side. It is not exactly in the middle. Okay.